All right, let's talk about something that is absolutely fundamental to writing good, efficient code. Big O notation. Trust me, understanding this is the key to making sure your apps don't just fall over when they get popular. So, let's dive right in. You know that feeling, right? You've built something. It works perfectly with your little test set of maybe 10 items. It's snappy. But then you throw a million items at it in the real world, and suddenly it grinds to a halt. What is going on there? Well, the answer to that mystery and the secret to writing code that can actually handle massive scale is understanding a concept called Big O notation. You can think of it as the universal language for talking about how well an algorithm performs. To really get what Big O is all about, we don't need to start with a bunch of complicated math. Nope. Instead, let's kick things off with a super simple analogy. Think about it like this. If you're driving to the corner store, it really doesn't matter if you're going 60 or 65 miles per hour. The difference is seconds, right? But what if you're driving all the way across the country? Now, that small difference in speed adds up to hours, maybe even a whole day. Big O is all about analyzing performance for that cross-country trip. It cares about what happens when your input size gets really, really big. So if we're going to put a formal definition on it, Big O is how we describe the growth rate of an algorithm. We're not measuring the exact time in seconds. Instead, we're asking, as our input gets bigger, how much slower does our program get? And crucially, we're usually looking at the worst-case scenario. We want to know the absolute slowest our code could be. Okay, now this might sound like it's about to get complicated, but here's the beautiful part. Analyzing Big O really just boils down to two incredibly simple rules. These rules help us cut through all the noise and focus only on what truly impacts performance at a massive scale. And here they are. It's this simple. Rule number one, we drop the constants. Why? Because just like that 5-mile-per-hour difference on a short trip, constant factors just become totally insignificant when the input size is huge. And rule number two, we only keep the dominant term. That's the part of our calculation that grows the fastest. And this makes it crystal clear. Let's say we analyze some code and find out its performance is something like n squared plus n plus 1. We just simplify that all the way down to O of n squared. Because think about it. If n is a million, then n squared is a trillion. The other parts, a million and 1, they're just a drop in the ocean compared to a trillion. The n squared term is the only thing that really truly matters. So, with those rules in mind, let's organize these ideas into something we can call the complexity ladder. This is basically a hierarchy of the most common Big O types, and it gives us a super clear picture from incredibly fast all the way to impossibly slow. At the very top, the absolute best you can get is O of 1, or constant time. This is the holy grail. It means your code takes the same amount of time no matter how big the input is. From there, we step down the ladder to logarithmic, linear, and so on, all the way down to the bottom with exponential, which becomes unusable almost immediately. As a developer, your goal is always to stay as high up this ladder as you possibly can. So what's the actual difference? Let's go back to an old school phone book. A logarithmic algorithm, or O of log n, is like doing a binary search. You open the book to the middle, check if the name is in the first or second half, and then you throw away half the book. You find the name incredibly fast. A linear algorithm, O of n, is like starting at the letter A and reading every single name until you finally find the one you're looking for. Now, the jump from linear to quadratic, this is where things get really dangerous. A linear O of n algorithm is just one simple pass through a list. Easy enough. But a quadratic O of n squared algorithm, that's usually a loop running inside of another loop. That means for every single item in your list, you have to go through the entire list all over again. This is where performance can absolutely fall off a cliff. Okay, so we've got the theory down, but what's the real-world payoff here? Why should you really, truly care about staying high up on that complexity ladder? Well, for starters, if you're looking for a job in this field, this number should get your attention. Big O notation and complexity analysis? They come up in over 90% of technical coding interviews. It's a skill you just have to know. But it's not just about interviews. I mean, just look at these numbers. For an input of 1 million items, a logarithmic algorithm, it's about 20 operations. A linear one takes a million. But look at the O of n squared algorithm. It takes 1 trillion operations. That's not just a small difference. That is the difference between an app that works and one that is completely and utterly broken. Let me put that a different way. That O of n squared algorithm that felt instantaneous, It took just 1 second for 1,000 items. For 1 million items, it would take over 11 days to run. That is the terrifying power of a bad growth rate. By contrast, a better algorithm, maybe an O of n log n, might just take about 20 seconds for that same million items. This chart just says it all, doesn't it? The bar for the 20-second runtime is so small you can barely even see it next to the skyscraper that represents 11 plus days. This is the choice you are making every single time you write a loop or pick a data structure. It's a huge deal. So let's wrap this up. Here are the key things you absolutely have to remember. First, big O is about the growth rate, not the raw speed in seconds. Second, always focus on that dominant term, the part that grows the fastest. And finally, keep in mind we've mostly talked about time complexity here, but all the same logic applies to space complexity, which is how much memory your algorithm uses. Both are critical for building great software. So I'll just leave you with this final thought. Think about the last piece of code you wrote. Can you analyze it right now? What was its big O? Finding where those performance bottlenecks might be hiding as your project scales, that is the first step to writing truly professional, scalable code. Thanks for tuning in.